Hello, everyone, and welcome to my presentation on interdisciplinary modeling of planetary habitability as part of the Habitable Worlds 2021 conference. My name is Rory Barnes. Before I get started, I want to direct you to the list of names at the bottom of the screen. This is the interdisciplinary team of scientists that helped me with the work you're about to see, and I'm very grateful for all of their contributions. If you participated in the pre-conference activities, you saw this figure, the so-called planets are hard diagram. I actually want to show you the original version of this figure, which I created just about exactly 10 years ago. The content is about the same, where the black squares represent general properties, the green ovals represent observable features, the orange triangles are what I like to call inferables, or properties that can be deduced from the observables and the laws of physics. The red octagons are the theoreticals, which are properties that can only be characterized via theoretical modeling. The reason I wanted to show you this version is because it includes these dash curves, which represent interdisciplinary connections between the phenomena. While daunting, this figure is also a roadmap for interdisciplinary modeling of habitable planets, and indeed, we used it to guide the development of this new software package we call vPlanet, which is a single executable that enables the simulation of magma oceans, the thermal evolution of terrestrial planet interiors, including their geodynamo and volatile or geochemical cycles. There's also a one-dimensional energy balance model for climates, atmospheric escape. There's obliquity and orbital oscillations due to planet-planet interactions, tidal effects, stellar evolution, including flares and activity, and finally galactic perturbations on the planetary orbits. Now, this code is not just simulating these processes in isolation. You can couple them together to perform the interdisciplinary modeling. This code is available to you. You can find it at this URL on the Virtual Planetary Labs GitHub site. So let's now turn to some recent research on this front. So first I want to look at circumbinary planet evolution, in particular in which a system where the binary stars are tidally interacting such that their orbit circularizes and decays over time is shown schematically on the left. The right panels show an example case for a planet orbiting two low-mass stars. The top panel is an installation. Initially, it's varying mostly due to the stellar evolution as the stars approach the main sequence, but at later times, you can see that the amplitude of the installation oscillations damps, and that's due to the back reaction of the planet due to the orbital changes of the binary star. And you can see the actual evolution of the semi-major axis and eccentricity in the bottom two panels. If you're interested in this work, I encourage you to go check out the paper from David Graham, which is in press and available on the archive. Next, let's turn inward to the magma oceans of the TRAPPIST-1 planets that are in the habitable zone. The left, again, shows a schematic for this model. It's quite complicated, but briefly, stellar radiation impinges upon a planetary atmosphere, warming the surface, but also driving the photolysis of water and hydrogen and oxygen escape. The freed oxygen can also be absorbed into the magma ocean, where it can bond with iron and precipitate out, thereby reducing the atmosphere. The mantle is also powered by radioactive decay and tidal heating and solidifies from the bottom up. The right shows some results from some simulations in which we plot the final water and oxygen content as a function of initial water content at the end of the magma ocean phase. As expected, planet E loses the most amount of water and builds up the most amount of oxygen, but crucially we see that water and oxygen could be present in all three planets. If you're interested in more about this research, I encourage you to check out the paper from Patrick Barth, which is also available on the archive. Finally, let's turn to climates and ice sheets in the galaxies. In this case, we wanted to explore what the distribution of ice is on planets in the habitable zones. So we performed Monte Carlo simulations in which we placed planets in the habitable zones of FGK stars with initial obliquities as predicted by planet formation. In other words, there's a peak near 90 degrees of obliquity. We applied an eccentricity distribution that matches the known exoplanets, and then we applied oscillations to those properties. Basically, these are Exo-Milankovitch cycles. At the end of 1 million years, we find that most planets are ice-free, but intriguingly, we also find that ice belts are about twice as likely as ice caps when ice is present. The ice belts that we formed are shown on the right in this paper from Caitlin Wilhelm that's under review. You see the trend immediately that planets orbiting K-stars tend to have much more and much larger ice belts than those orbiting F-stars. This is just due to ice's different reflective properties as a function of wavelength. Essentially, if an ice belt on an F-dwarf planet reaches about 20 degrees from the equator, it collapses into a snowball due to the ice albedo feedback. So to summarize, here are some statements that just reiterate what I just said. I want to direct you to the italicized statement at the end of this slide. There's a bit more on these methods at this meeting. If you're interested, you can see Rudy Garcia and Lauda Amadal's posters on geochemical cycles and stellar activity. And finally, I just want to invite all of you to the first vPlanet Developers Workshop, which will take place this June. If you're interested in learning more about vPlanet, it's free, it's virtual, it's open to everyone. You can learn more about this by following the code on Twitter or emailing me directly. Thanks for your attention, everyone. Stay safe, and I hope to see you in June.